Let's take a look at principles of rainwater infiltration control. Exterior walls are one of the major determinants of the appearance of a building. They convey images such as strength or solidity, lightness or openness, or a sense of movement or activity. In terms of the building's performance, the importance of exterior walls is even greater. Together with the roof, they constitute the building's envelope, providing the separation between inside and outside and serving to maintain an acceptable interior environment. The exterior walls can serve the envelope function only if they are able to perform well under a range of environmental conditions. They must prevent water infiltration from rain and snow. They must control heat loss and heat gain. They must control air leakage and water vapor transmission. They must resist fire. They must control sound transmission. And they must accommodate movement due to thermal, moisture, and other causes. Let's take a look at rainwater infiltration control. Three major forces that affect water infiltration through the exterior walls are gravity, the capillary effect, wind. Because these forces frequently act on an assembly simultaneously, multiple strategies must be used in the same assembly to counter water infiltration. Gravity generally affects water penetration through an exposed horizontal surface of a wall and can be countered by providing a nominal slope in the surface. The purpose of slope is to drain water away from vulnerable parts of the building. Thus, a roof overhang protects the upper portion of the wall, and the coping on top of the masonry fence is sloped on both sides of the wall. The coping over a roof parapet is generally sloped towards the roof so that water drains on the roof. In exterior window sills and thresholds under entrance doors, the slope is directed away from the building. Water molecules are subjected to forces of attraction between them, creating an intermolecular cohesive bond between them. In addition to the cohesive bond, water molecules experience forces of attraction from the molecules of the surface with which they are in contact. These forces create an adhesive bond. For most building surfaces, the adhesive bond is stronger than the cohesive bond. It is because the stronger adhesive bond that the thin film of water is able to travel horizontally along the soffit instead of dropping vertically by gravity. A drip mechanism, which consists of either a continuous groove or a vertical projection, counteracts this phenomenon, shown in the figure that's attached. Cohesive and adhesive forces also create the capillary effect, which is responsible for suction forces that occur in tiny spaces between two surfaces. In this case, the water is sucked between the surfaces. Capillary suction can also occur in a joint between two non-porous materials if the joint is narrow. In narrow joints, capillary suction can be prevented by introducing a larger space, nearly a quarter-inch or wider, immediately beyond the capillary space. This space is referred to as the capillary break. Providing an overlap between members meeting in a joint is another common sense measure. The force of wind can impact kinetic energy to water, causing the water to travel horizontally as well as vertically in the joint. Therefore, the overlap must be sufficiently large enough to present a reliable baffle against wind-driven rain. A lapped horizontal joint performs better than a lapped vertical joint, because the water has to work against the force of gravity to get in and across the overlap in a horizontal joint. Capillary breaks can also be included in a lap joint. A horizontal butt joint can be made infiltration resistant by incorporating L or Z flashing. L or Z flashing consists of an impervious membrane that provides a barrier to water and directs it to the exterior surface. Various types of sheet materials, galvanized steel, stainless steel, copper, lead, and polyvinyl chloride, PVC, are used as flashing materials. Filling joints with sealants is another commonly used strategy to keep water from penetrating through the joints between building components. Because sealants degrade over time from exposure to environmental factors, particularly solar radiation and water, they should not be relied upon as the only water-resisting element. A certain amount of redundancy must be built into the detail in case the sealant fails. Usually, all or most of the strategies previously discussed are used in a single detail, as shown in the section at the sill level of a typical wood window. Let's take a look at rainwater infiltration control and exterior walls. Water-resistant exterior walls may be divided into three types: walls with overhangs, barrier walls, and drainage walls. Walls with overhangs. This type of wall system depends on protective floor and roof overhangs to prevent water infiltration. It has limited application because the overhangs are required to shield the wall completely from wind-driven rain and therefore must be quite deep. In addition, the overhangs impose economic as well as design constraints on the exterior envelope, particularly that of a multi-story building. However, a shallow roof overhang is commonly used in low-rise building and can provide substantial protection from water penetration at the wall-roof junction. A barrier wall is a wall that functions as the primary structure and at the same time performs as the building envelope. CMU load-bearing structures are examples of this wall type. This wall type resists water infiltration either by providing an impervious barrier to water referred to as a face-sealed wall, or by functioning as a water reservoir, a reservoir wall. An example of a face-sealed wall is a CMU or concrete wall system that with an applied water-resistant veneer, such as EIFS or stucco. On the other hand, an example of a barrier wall that acts as a reservoir is a porous masonry or concrete wall that is so thick that any absorbed water is unable to migrate into the wall's interior surface. The thicker the wall, the larger the reservoir. In this type of wall, only the outer layer of the wall gets wet. Even during a long rainy spell, given a long dry spell, the entire wall will dry again. Let's take a look at rain screen exterior cladding. A rain screen cladding system includes the basic principles of the drainage wall system, but it also addresses the issue of water penetration due to unequal distribution of air pressure on the exterior of the wall and in the airspace between the cladding and the backup wall. Because wind produces positive pressure on the windward wall and negative pressure on the other walls of a building, the air in a continuous airspace will circulate and move in and out through weep holes and other openings, joints, cracks, etc. in the cladding. This makes it impossible to achieve pressure equalization between the outside and the airspace. In order to reduce the suction of water in a drainage wall, the pressure between the airspace and the outside should be equalized as much as possible. Pressure equalization is accomplished by not completely sealing the cladding. In fact, providing weep holes and purposely incorporating other openings in the cladding help to create pressure equalization. If the openings in the cladding of a drainage wall such as weep holes, are few and small in area, the pressure between the airspace and the exterior cladding will not be equalized. In such a wall, although the airspace is under atmospheric pressure, the outside surface of the cladding is subjected to a pressure greater than that of atmospheric pressure. This will cause the water to be sucked into the airspace through the weep holes. Water will also be sucked into the airspace through joints in cladding that are inadequately sealed or have become leaky over time. Water suction will take place on the windward facade only because at this facade the pressure in the airspace is lower than the outside pressure. On the other facades, the airspace pressure is higher than the outside pressure, hence no suction takes place through non-windward facades. To prevent air movement within the airspace should be divided into small sections with continuous cavity closures, particularly at corners and floor levels. In summary, an ideal rain screen wall should consist of the following 3 water infiltration control features. 1. Voids in cladding for pressure equalization in the airspace. 2. Compartmentalization of the airspace. And 3. An airtight backup wall.